In this lecture, we are going to prove an important relation of numerical analysis relating to backward difference operator nebla and differential operator d, where d, this is d dx, this is differential operator, and the relation is nebla y n+1, this is equal to h into 1 plus half into nebla plus 5 by 12 into nebla square to so on delta y. We have to prove this relation. Now, starting from the left side, we first write nebla y n+1, and the definition of this is y n+1 minus yn, because we know that the definition of nebla f of x, this is equal to f of x minus f of x minus h. Okay. Now we write this is e of yn minus yn, because e is the shift operator and the definition of e is e of f of x, this is f of x plus h. Okay. Now this is e minus 1 into pi. Here we use two useful result of relation between operators. This is the relation between shift operator and differential operator, and this is also shift operator and nebla operator. And now put the value of e, this is equal to e to the power hd here. We already proved all the relation between the operators in previous 2 or 3 classes. Okay, you can see this proof and this proof also, and the link of this video is given in description box. Okay, now we put the value of e, this is equal to e of hd minus 1, this is into y. Now what is the series of e to the power x? E to the power x, the series of e to the power x is 1 plus x square by 2 plus x cube by 3 to so on to infinity. Okay, and sorry, this is factorial 2, this is factorial 3. Now we put here the series which is given by 1 plus hd plus h square d square by factorial 2 plus h cube d cube by factorial 3 and so on to infinity minus 1 into yn. This is not like this, this is yn. And here y must cancel out, and we taking common h from the left and taking common d from the right, because here in the proof there will be dy, so we taking common d from the right, and the remaining portion is given by 1 plus hd by 2 plus h square d square by 6 to infinity. Okay. Now from this relation, that is the first relation, we get e to the power minus 1, this is equal to e to the power minus hd, and putting the value of e to the power minus 1, e inverse, this is equal to 1 minus nebla, so minus hd, this is equal to 1 minus nebla, sorry, e to the power minus hd, this is equal to 1 minus nebla. Now taking logarithm on both sides, we get this is minus hd, this is log of 1 minus nebla, and the series of log is minus nebla square by 2 minus nebla cube by 3 and so on to infinity. Okay. Now hd is given by, this is minus once again, so all of them are positive. Okay. Now we put the value of hd from here in this relation, so we get h into 1 plus, this is half into nebla plus nebla square by 2 plus nebla cube by 3 and so on to infinity, plus 1 by 6 into again nebla plus nebla cube by 3, sorry, nebla square by 2 nebla square by 2, nebla cube by 3, nebla cube by 3, and so on to infinity whole square, and this term goes for infinity, and this is del dy. Right? Now we write this all the term in some arrangement. The first term is 1 because only one constant term, this is 1, and nebla to the power 1, we from this relation get only one nebla. This is nebla by 2. This is, and from this term, and so after this term there is no nebla to the power 1. So we write here nebla by 2, and we get nebla square term. From here we get 1 nebla square, this is 1 by 4, plus from here we get this is nebla square. So this is 1 by 6 into nebla square. Okay, nebla square, and so on. Since in the proof there is only of the term nebla square and no other term are given, so we get, or we write here to infinity, and the last is dy. Okay, and this is h into 1 plus nebla by 2 plus this is obviously 12, and this is 5 by 12 into nebla square, and so on to infinity. This is dy. Okay, and clearly this is the given proof, and the left side we write once again nebla y n+1. Okay, very simply but very interesting proof using d and nebla. Thank you for watching.